zeros of a linear polynomial. Hello, everyone. Today, we are going to begin a new topic in our algebra unit, zeros of a linear polynomial. Before we dive into the specific formulas and calculations, let's start with a brief introduction to the core concept. In our ongoing study of polynomials, you will find that the concept of a zero is absolutely fundamental. Now, you might be wondering, what exactly do we mean by a zero? Well, a zero of a polynomial, which you might also hear referred to as a root, is simply that specific value of the variable x that, when substituted into the expression, makes the entire expression equal to zero. Keep this definition in mind, because as we move to the next slide, we will apply this idea specifically to polynomials of the first degree. Understanding linear polynomials. Now that we understand the basic definition of a zero from our introduction, let's take a closer look at the specific type of expression we are working with today, the linear polynomial. First, what makes a polynomial linear? It simply means it is a polynomial of degree 1. In simpler terms, if you look at the variable x, the highest power or exponent attached to it is exactly 1. To work with these mathematically, we use a general form, which we write as p of x equals a x plus b. Let's break down what these letters represent. Both a and b are real numbers. However, there is one very important rule: a cannot be equal to 0. Think about why that would be. If it were 0, the x term would disappear entirely, leaving us with just a constant, and it wouldn't be a linear polynomial anymore. In this expression, we call a the coefficient of x because it is the number multiplying our variable, and we call b the constant term because it stands alone. Keeping this structure in mind is crucial, because in the next slide, we will use these exact components, a and b, to calculate the zero of the polynomial. Understanding the zero of a linear polynomial. Now that we understand what a linear polynomial looks like from our previous slide, let's walk through the actual process of finding its zero. If you have a linear polynomial, which we've written as p of x equals a x plus b, there is a very logical three-step method you can follow to find the value of x. First, step 1, we begin by setting the entire polynomial equal to 0. So, we write a x plus b equals 0. This is because, as we learned in the introduction, the 0 is the specific value that makes the expression vanish. Next, step 2, our goal is to isolate the term containing x. To do this, we need to move the constant term to the other side. We do this by subtracting b from both sides of the equation. Once we do that, we are left with a x equals negative b. Finally, step 3, we need to get x all by itself. Since x is currently being multiplied by a, we perform the opposite operation and divide both sides by a. This leaves us with x equals negative b over a. So, to wrap it all up, we can conclude that the 0 is given by the formula. 0 equals negative b over a. Keep this formula in mind, because in the next slide, I am going to show you exactly how to apply this to a concrete mathematical example. Illustrative examples. Now that we have understood the theory and the formula behind finding the zero of a linear polynomial, let's put it into practice with our first example. This is a pure mathematical calculation to help you get comfortable with the steps. Suppose we are given the polynomial p of x equals 3x plus 12. Our goal is to find the value of x that makes this entire expression equal to 0. Let's walk through the solution step by step. First, we need to identify our coefficients. If we compare our polynomial, 3x plus 12, to the general form we saw earlier, x plus b, we can certainly see that it equals 3 and b equals 12. Next, we apply the formula we just learned. We know that the 0 is found using x equals negative b over a. Now, we simply substitute our specific values into that formula. This gives us x equals negative 12 divided by 3. When we simplify that division, we get our final result, x equals negative 4. But as a good mathematician, you should never just stop there. You should always verify your answer. To do this, we take our result, -4, and substitute it back into the original polynomial in place of x. So p of -4 becomes 3 times -4 plus 12. This simplifies to -12 plus 12, which equals 0. Because the final result is exactly 0, we have mathematically proven that -4 is indeed the correct 0 for this polynomial. This same logic of substitution will be very helpful when we look at how these polynomials apply to real-world scenarios in the next slide. Illustrative examples continued. Now that we have mastered the pure mathematical calculation in the previous example, let's see how this concept actually applies to a real-life scenario. This is what we call a real-world application. Imagine you have a candle that is 20 centimeters tall. As time passes, it melts at a constant rate of 2 centimeters every hour. We can actually represent the height of this candle using a linear polynomial, where t represents the time in hours. Our polynomial, which we'll call h of t, is equal to -2t plus 20. Notice how the negative sign represents the decrease in height. Our goal here is to find the specific time, t, when the candle has completely melted. In mathematical terms, this means we are looking for the 0 of our polynomial, the exact moment when the height becomes 0. Let's walk through the solution step by step. First, we identify our coefficients by comparing our equation to the general form we studied earlier. In our equation, -2t plus 20, the value of a is -2, and our constant term, b, is 20. Next, we set our polynomial equal to 0, so -2t plus 20 equals 0. Now, we apply the formula we learned on the previous slide, which is t equals -b divided by a. When we substitute our values, we get t equals -20 divided by -2. When we simplify that division, the two negatives cancel each other out, and we are left with t equals 10. So, to conclude our calculation, we can determine that the candle will be completely melted after exactly 10 hours. As you can see, finding the 0 of a polynomial isn't just an abstract exercise. It helps us predict exactly when a change will reach its conclusion. In the next slide, I will highlight some common pitfalls to watch out for so you can apply this method accurately every time. Common mistakes to avoid. Now, before we wrap up our lesson and move on to our final summary, I want to pause and discuss some common pitfalls. Even when you understand the formula, it is very easy to make small mistakes that lead to the wrong answer. So, when you are calculating the zeros of linear polynomials, please be mindful of these 3 specific errors. First, watch out for sign errors. This is perhaps the most frequent mistake students make. It is very easy to forget that negative sign in our formula, -b over a for instance. Let's look at the polynomial p of x equals 2x minus 6. If you forget the negative sign, you might get the wrong result. But if you apply the formula correctly, you take -6 divided by 2, which simplifies to 6 divided by 2, giving us a final answer of 3. Always double-check those negatives. Second, ensure you are correctly identifying your a and b values. It sounds simple, but in the heat of an exam, it is easy to swap them. Always remember that a must be the coefficient attached to the x, and b is your constant term. Finally, be careful not to confuse the order of your division. You must divide the constant term by the coefficient of x, not the other way around. Keep these tips in mind, and you will find that finding the zeros becomes much more reliable. Now, let's look at our final slide to recap everything we have learned today. Key takeaways. First, remember that a linear polynomial is defined by its degree, which is 1. As we saw in our earlier slides, it always follows the general form, p of x equals a x plus b. Second, it is crucial to keep in mind the definition of a 0. As we discussed when we first introduced the concept, the 0 of a polynomial is simply that specific value of x that, when plugged into the expression, makes the entire polynomial equal to 0. Third, we have learned a very handy shortcut. Instead of always working through the algebraic steps of isolating x, you can use the direct formula to find the zero, which is x equals negative b over a. Finally, a key property to remember for your exams is that a linear polynomial will always have exactly one zero. It won't have 2 or 3. It is always just one unique solution. All right, we have reached the end of our lesson. Let's take a moment to recap everything we have covered today so you can consolidate your understanding. I hope this summary helps clarify the topic. If you have reviewed the examples we worked through, such as the melting candle problem, you should now feel confident in identifying and calculating these zeros. Great job today!